So my name's Peter Evans. I'm from Lidar, and I'm just going to have a chat about geotechnical analysis of Raisebores using Lidar data. So we'll go through the scanning process as we're doing it now, failure mechanisms that we're able to see in quite good detail, talk about some stress orientation, volume of overbreak, and raise assessment back analysis. So to capture the data, we can either winch, fly, or boom mount the scanner. So in that sense, just the boom mount, just sort of talking about pushing the boom out over a vent rise or shaft. So that's our winch box and the boom. Scanning with the winch methodology, trying to make it easy for ourselves. If the pilot hole's still in place, tends to be the quickest and easiest way to capture the data. Removes the need for operating close to open holes. The scan's central to the shaft. Not that that's a particularly critical issue, but as you if there's deflection in your rise, etc., you end up bumping against the end of the rise, which just induces shadow. The boom, again, pushing the boom out over a vent rise, either at the top or bottom. As I said, the scan may not be central, and the boom just allows to stand off the rise and keep people away from the open hole. Flying is possible. I don't think there was, so the issue with flying up raises at the moment with slam-based LiDARs, especially when they're particularly smooth, is that they tend to get lost in the shaft because in order to determine its location, it needs features that it can see, and as it moves away from objects, primarily as you move further and further up the rise, you see less and less points at the bottom of the rise. Eventually it gets to the point where it just sees a smooth pipe. Yes, it knows it's moving up or down, but it starts getting confused about how far up or down it is. So it is possible, but there's a limit to how far you can go. In blast hole rises, you don't really have those issues because there's a lot more features that it can actually understand how quickly it's moving up and down, etc. So the other one is depending on how big your rise is. There's a limit to its field of view. So you can't really see scale here, but that's a flight up a rise. So going. I'll carry on. Flying up a rise, and so that was the data that we captured with that same flight. So again, in that sense, you do start getting the same issues that you get with CMSs and the like, where eventually you get to a point where you'll start getting shadowing and things like that. You're in a 4.5 metre rise, and so your field of view is narrow. So then, from the scanning data that we're getting now, we can start to actually see some of the failure mechanisms that we're getting in those rises. So the left is the video of the scan, and I've just tried to align the same points to see what happens. So the hot colours, the reds, the yellows through to reds, are where the rise is larger than the design diameter, and the cold are where it's smaller. And I guess on the video, or on the image on the left, you can certainly see, you've got breakout and the like. You can see those blocks, but it's much harder to actually quantify what's happening. You can look down that rise and you think primarily that it all looks to design by and large, but with the scanning data we can actually start to see that we're getting the spalling, we're getting the actual buckling around the edge of that spalling, so we're actually getting, the diameter is smaller. Yeah, again, you can see those slabs buckling off the side, etc. You can actually start to see how irregular the surface of the rise is during that cutting process. Yeah, same as the last one. So this is plotting intensity. So being a lidar, you get the light source, so you get your distances, but you're also getting the actual reflectance off that surface. So then you can start seeing what's happening from a number of different perspectives. So here in a rise where things are smoother, you get a higher reflectance off that. Where it's broken out and it's rougher, you get less, so you get that contrast. Depending on lithological units and the like, you can get the changes in lithology if there is a contrast in their reflectance. Water is another one that tends to show up, and I've got an image of that a bit later. So again, a bit more just on the raise damage side of things. So you've got, again, the same colour scheme, the blues and the reds. You can really see in the top left of that image, you're getting buckling, so that material hasn't actually fallen out yet. And then on the opposite side, you are getting that material has actually fallen out. And then in some cases, these are really sort of primed, ready to go, but haven't actually come off the walls yet. Again, this is a plot of intensity, but with just a grey-black colour scheme. But again, you really start to understand which structures are actually causing your fallout or your failures. Map those structures. Okay, it's maybe not going to, well, you can do some kinematics on this to try and understand whether it's going to propagate further, but then also understand how that's going to impact future rises. I struggle to get nice pictures of this, and that one in the middle looks even worse than on my screen. But anyway, look, obviously, there's plenty of structural data that can come out of this, and again, the primary purpose there being inform, the next rise that you're doing, what's actually inducing failure in your rise, which structural sets are causing those issues, and then of course you also get a combination of mechanisms that ultimately cause the failures, so the structural and the stress-driven failures. This is the same image that I showed previously. I guess where this became particularly valuable at this site was an elastic model of their, what they believed was their stress regime would mean breakouts to the top right and the bottom left, and you can see pretty clearly in the LiDAR image that's about 90 degrees. They had multiple stress measurements. Most of them pointed to this stress regime. They did have another stress regime or some results that showed this orientation. And so that's the breakout that they were seeing there. I guess tongue-in-cheek, but obviously the one on the right, based on ground truthing of observations that you're actually getting, is your stress field, or certainly closer to. For sure, this is two-dimensional. Depending on what your actual stress regime, things can get more complex, but it's still an important validation. Look, I just thought this was quite interesting. So video down the rise on the left, And yeah, I think just not something you get to see every day. But yeah, the breakouts here, you can quite clearly see in the image, although not now that I've drawn a big line on it, a structure that runs through that rise. And as you sort of watch the video go down, you could really see the rotation of that spalling around that structure. So I just thought that was interesting. So yeah, it gets rotated and then comes back onto its original orientation. So yeah, we've got some further work there. Yeah, we've got some data. Yeah, we've got some UCS testing in that rise. So yeah, we'll probably have a look at how those actual local results occur, relate to actual breakout depths. I know there's been a lot of work on that. There's papers about that. So yeah, we'll have a play with that and see what we get. Again, I guess it starts getting interesting there where you can't necessarily determine the full depth of failure, especially where you've got sections that are buckling but haven't actually fallen out yet. And then yeah, we want to try and just replicate that stress rotation, the spall out rotation as well. Again, probably goes back to the previous image, but you're getting a better understanding of all the behaviours within the rise. That stress breakout, but then either side of that tends to be an area of compression, so reducing the rise diameter, and then actually down the very bottom of that rise was where some more of the structural issues happened, and I've cut that off, but it gets worse as it goes down. So then we can look again in a bit more detail around what exactly is taking place within the rise. So this instance was basically taken sections every 0.25 of a metre, and then we're able to quantify, I guess, roughly how much material has come out of the rise. Again, the stuff that's still hanging up there and the like. So over this rise, about 180 cubic metres of overbreak, and so about 7% total over the entire rise length. But you can see from the graph, basically from 100 metres down to the bottom of the rise is where things really get much bigger, and that was a combination of structural failure and the stress-induced damage. So basically 95% of that 180 cubic metres came from that bottom 45 metres, and the overbreak in there is about 23% in total. So at the very top of that chart, there's that section of negative overbreak, but just sort of trying to focus on that. So this is an unrolled image of the rise, and you can see that just the amount of areas that are under compression, perhaps started buckling, etc., but haven't actually fallen out, which is actually causing that negative value. It's fractions of a percent, 1% type number. It's pretty small, so not really a big issue in the grand scheme of things. The other one that came out here, you can see these ellipsoids, and there's actually another couple there as well. But these were really pronounced, very flat, steep planar structures, which actually look really nice in a wireframe. But they just really stood out there. So they're fairly easy to map structures like that. So just quickly going over another site where we did some work. Basically, it was a rise that was excavated, they had excess material reporting at the base of the rise. They'd had a situation where they knew they had some faults through the rise. They pulled the reamer head up. When they were actually lowering the reamer head down, they had a situation where it actually sort of hung up in the rise, and so there was a concern that this fault area had failed, and therefore whether they needed to spray the rise. So that doesn't show up very well. Looks much better on my screen. So look, I think the key thing to see here is this is where the actual structure came through, and basically there was no significant overbreak outside of the design. There was a couple of sections up to 0.8 of a metre larger than design, but they were fairly concentrated. See if there's the rise was wet, so bottom of the rise was a fair amount of water coming out there. It took me a while to actually find this because there was noise inside the rise, because again the Lidar will reflect off water, so there was water coming out of the rise, and it wasn't until I actually basically cut the rise and sort of went, oh okay, that's just water coming out of a structure in the side of the wall. And there was also, you can actually see again from the intensity, the actual specific structures that actually then started bringing water into the rise. So there was two structures that started producing water, and then a third structure, and basically beyond that third structure the whole rise was saturated. Once the whole rise is saturated, then you're not really going to see any more. Again, similar process to what has been done that I've already shown. So basically we could show that over the entire rise, we're looking at about 60 cubic metres of material, and in fact, so that's where the excess material is coming from, and that equated to about 3% overbreak over this entire rise, so it wasn't really a major issue, and so basically I could then make a decision to not, I've ruined the punchline at the end, but so then we also did some back analysis of the empirical work, and yeah, we were getting pretty good correlation where basically where the max span was deemed to be lower, we were starting to see higher levels of or smaller diameters, higher levels of overbreak in the rise. I guess the correlation there being, whilst the rise was stable, and the empirical assessment was saying yes, it's stable, stable doesn't mean no fallout, etc. So it's just a correlation between those two factors that can possibly inform, give a better understanding for future rises. And yes, the final outcome was to not spray the rise, so obviously that saved them a bunch of money. So raise scanning outcomes. The scanning rises is much easier now. I remember scanning a rise 15 years ago or something, and it was a single axis laser that would scan every 3 meters or something like that in an arc with a point every couple of degrees type thing. The sort of richness of information now is orders of magnitude higher. From an asset management perspective, the cost of scanning a rise is a bit over 1% of what it costs to, say, excavate a 200 metre long, 4.5 metre Raisebore. So by scanning your rise, it just gives you an opportunity to actually have a better understanding of what's happening if you have any issues in the future. Ideally you don't. Again, the case I put forward before, the cost of scanning a rise is less than a single stress measurement, and that's a lab stress measurement. And it provides a ground truthing, it's actual observation of what's happening, and I think it becomes useful where typically your infrastructure raised bores are generally a bit further away from excavations, generally earlier before stoping is happening and the like, so it just gives an opportunity to actually see, to validate what's happening. Can't give you magnitude, can't give you K ratio, so keep doing your stress measurements, but it's just an opportunity to actually a very clear validation point. Structures, causing your failures, again, better inform your future rises, understand where your actual, what are your critical joint sets, which ones are actually causing you issues. Again, same case in point, back analysis of raises to actually validate the empirical assessments that are primarily still the primary methodology of assessment that we see. But understanding whether your future rises are going to have issues or not. Certainly, one of the last rises we did, it really starts to push you in a direction where you say, well, is this diameter still viable? And again, I'll just say, those areas where you're getting 20% over break, is that viable to keep going at that diameter deeper and deeper? And certainly if you're planning on putting an escapeway inside a rise, that's probably we think it's a sensible idea. Look, I spoke fairly just about Raisebores and the like today, but obviously there's ore passes and shafts and the like that are also viable. This was a case where there was two flights, flight from the bottom, flight from the top, because access into the intermediate levels wasn't possible, so this is a blasted rise, but it just enables them to understand from an asset perspective how things have changed from those original CMSs that were done when these were excavated, how they're deteriorating. Is it going to be something that needs to be addressed in the short, medium or long term? This is a failure that we scanned, and this is the sort of case in point around that intensity. So very clearly there's an intrusive dike through this this failure, and that's where the intensity can actually help to identify what's changing. And you really can't see it in here, but there's actually a fault that runs through here, and you can actually see the offset in that structure through there. So it just gives you the intensity actually provides a big jump in information. Bolt plates. We scanned a mine and we sort of picked out, it's like, oh, well, you've rehabbed this 20 metres, and it was just because there was new shotcrete on old shotcrete. So you just get a contrast in intensities. Tracking rehab, where's been sprayed, where hasn't been sprayed, and if you've got a bridge in your backyard, then we can scan that as well. This was just for interest, for a bit of fun. So this was, we did 4 flights around this and merged them together, and a walk across the middle. And then just a pretty picture of one of those, of a rise that we scanned as well. So that's about all I've got. So thanks very much. Any questions, and whether I can figure out how to turn the lights on. Yeah.
Technology.
While you're fiddling in the dark there, what you say is we can use this for stress testing. When you winch down a vent race, is there auto correction, or do you do post processing for the rotation?
So the rotation is not a not really an issue. So